This is a UTME physics question, and then it's under simple harmonic motion. The question says that the velocity of a simple harmonic motion is given as v equals 8 square root of 25 minus y squared of a system of mass 2 kilograms. What is the total energy of the system? So basically what we need to do here is that we need to first of all determine what are the things that we were given. Obviously, everybody would see here that the mass given is 2 kilograms. But exactly what are we going to use this equation for? This equation that was given right here, what are we going to use that equation for? Now, one thing you should know is that the general model of the velocity of an object in simple harmonic motion can be represented using this particular expression here. Now, some of you, instead of y, you might have seen x in your textbook. It doesn't make any difference. This is the velocity of any object in simple harmonic motion. This omega right here signifies the angular speed, and a here is the amplitude, while y is the displacement. Sometimes you can see x in the expression. So that is exactly what you need this equation for. With this equation, you can get a lot of information from that. So you can get your v or whatever the case is. Now, but let us rewrite this equation like this. So this implies that if I write this equation, v equals 8, then you have square root of 5 squared minus y squared. Now, what does this tell us? If you compare these two expressions now, so you can see that the omega, so this is not pertaining to this question, but you can easily bring out your omega here, which is your angular speed. That will be 8 rad per second. And also the amplitude of the motion will be 5 meters. So I'm assuming that this is measured in meters, in standard units actually. So, but that's not our problem in this problem. That's not what we have to do. The problem says that what is the total energy of the system. Now, one thing about a body in simple harmonic motion is that, for example, if the body was a simple pendulum, let me draw this. So we would know already that there are basically three major positions that we always connect. Of course, there are other positions. We have this point here, this point here, this point here. At this point, we know that only potential energy is maximum and the kinetic energy is zero. The same thing is here. And at this point, it has only kinetic energy. Based on the principle of conservation of energy, energy is conserved throughout. Some of the mechanical energy here is the same as here, is the same as here. But the good thing is that if we can only get the potential energy here, then that will be the total energy, since there's no kinetic energy in this place. And in this place, if we can get the kinetic energy, that will be the total mechanical energy, since there is no what? There is no potential energy here. So, and at this point is known as the equilibrium point. This is the equilibrium point of the simple harmonic motion. And what happened there is that the displacement right there is zero. That is a point where y is 0. So if I put that in this equation, that would imply that v equals 8, then multiplied by square root of 5 squared minus 0 squared. Of course, you know that will go. Then this goes. That implies that v is going to be 8 times 5, which is 40 meters per second. So the total energy that is in the system can be calculated just using the kinetic energy when there is no displacement at all. So the kinetic energy will be the same thing as the total energy of the system. So that will be 1 over 2 mv squared, which is multiplied by 2 multiplied by 40 squared. And if you do that very well, that will be 1,600 joules. And that solves the problem. Mind you, the reason why I'm able to use the kinetic energy as the total energy here is because I went to consider a situation where the displacement is 0. And since the principle of conservation of energy says that total mechanical energy will always be conserved. So at this point now, there is no potential energy, which is 0. So 0 plus kinetic energy, which is the total energy, is still the same thing as saying that kinetic energy equals total energy at this point where the displacement equals 0. And that solves the problem. I'll see you in the next one. Don't forget to subscribe and follow as well.